So once again, I want to welcome you to this class, and we're going to be looking at storage virtualization. Previously, we have looked at compute virtualization. We have also looked at network virtualization, and today we want to, look at storage virtualization basics. We are aware that these virtual machines we are talking about, they must be storing their information or their data somewhere, because they can't store data just there in the space. That data has to be stored somewhere. And even today we have quite a number of devices that we use to store our data on our computers, and some of it being the hard disk. And hard disks are, very important part of our personal computers, either whether you're using it on a laptop or on your desktop. You need to have that kind of storage for you to help you, you know, store your devices. And that's why even when you're buying computers today, the first thing you need to check out was most of the times what people concern themselves with: what is the capacity of my storage, of my storage. And then even when you're buying a phone, nowadays you're concerning yourself, how many GBs, what is the storage capacity? Because this is where you're actually going to be storing your devices. And to date, even people go an extra mile of not only just even looking at the capacity, but also looking at the performance of the hard drive. Is it an HDD or is it a solid state? What is its, read and write speed? Today, that people are also concerning themselves uh, to that extent. So in cloud computing, disks also are important. And we also need to know that the disks in cloud computing are not physical, because for us now, if it is in the cloud and I am storing my files, all my files, I'm backing them up and they're in the cloud. Therefore, that disk in cloud computing is somehow not physical in that kind of sense. So users of cloud, or you as network engineers, you need to not only concern yourselves with the disk performance, but also the capacity and also the physical attributes. That's why as you as a network or a cloud engineer, you only need to not look at the end user's concern, but also know, because you're the person who is going to be putting up those resources together. For people like me who want to back up my files in the cloud to access that storage over in the cloud. That's why we want to look at storage virtualization products. As you are aware and as you agree, data has become an enterprise most important asset today, and many companies which rely on data are actually earning a lot of money. So how this data is stored in the cloud, how this is different from the way it is stored in our traditional way, we want to look at those things and want to get answers from those things, or to those things in this chapter. So upon completion of this course, we shall be able to understand Huawei's Fusion Sphere virtualization solution. We'll also be able to understand the storage architecture used for virtualization environment, and we'll understand the different types of disk. We'll understand the differences between centralized and distributed, and also we understand the differences between virtualized and non-virtualized storage, understand the different types of virtual machine, and lastly, understand the storage features of Huawei virtualization products. So storage architecture, we want to look at the storage architecture for a virtualized environment. As you can see, as I'm going to show you, physical disks are usually located at the bottom layer, and cloud disks are usually located at the top layer. Let me just run this pretty very fast, and we're asking ourselves now, how are virtual machines going to be able to get these resources, the SSD, the hard disks, the network, attached storage, all the, the storage, the sun, or maybe the different disks on the network, or even our distributed storage. How are our virtual machines going to be able to access those things stored in the cloud? So we're asking ourselves, how do virtual machines access the underlying storage resources? We know that our virtual machines are created on top of a hypervisor inside a computer, which which computer is also having its resources. So how are they going to be able to access those resources, minus affecting the functionality of that parent host? So in this chapter, we want to focus at storage virtualization. This is the architecture for a virtualized environment. And as you can see, we can either have a virtualized storage, or we can virtual machines can access this in a non-virtualized storage. When it comes to a virtualized storage, usually we have our disks at the bottom layer. These are our physical disks, which can either be raided or replicated. They can be either raided or replicated, and after them, putting all these disks together, they could be 1 TB, 2 TB, depending on your capacity and depending on your needs. After putting them together, we can either choose to use SAN, or we can also choose to use the NAS storage. We're going to look at these things later on in details. And if we are using SAN, one thing you should know, SAN is not a block level system, and therefore it has no file system. But if you're using NAS, it has a file system, and we shall be looking at those things later on in detail, but don't worry about yourselves. But what it is important for you to take out from here, we have our physical devices lying at the bottom of our architecture, and we have our virtual disks here lying at the top layer of our virtual machines, the virtual machines to access the different resources. So this is basically how the architecture is. You have your physical resources. These physical resources are rated or replicated to come up with a storage pool. And this storage pool now here, we can either go ahead and NAS helps us to it comes with a pre-configured file system. Whereas if you're using SAN storage, then we go ahead and create logical volumes, what we shall be calling logical unit number, or what some people in our language call partitions, right? After coming up with our logical partitions, then we can add a file system if you're using SAN, and then we come up with our shared catalog. This shared catalog, there are different file formats or file systems depending on the hypervisor you're using, but these are like the virtual disks where our virtual machines are going to be getting our virtual machines. We shall be also looking at some of these file formats later on, file system formats, and also in a non-virtualized environment, still we have our distributed storage here. We can do the replication to come up with a distributed storage, add a logical division here to come up with our logical unit number, or if it's just a normal physical disk and you're not doing any kind of virtualization, just go ahead and add a logical division. That is maybe by partitioning it, have your logical unit number, and then the hard disks are available for our virtual machines to access the resources. Okay, so when you are actually formatting your hard drive, many of us think that it equates to erasing data, but yet in the actual sense, you are formatting the hard drive and you're giving it a file format that is supported either by that operating system, or in this case, if it's a virtualized environment, supported by that hypervisor, isn't it? That's why when you go to your operating system and let's say you want to format a given file, and let's say I was tired of this drive and I was going to use it in another environment, and I wanted to go ahead and format my drive here, which I call server X. I go ahead and format it, and I go to format. When I go to format, I have different options. Too bad I can't make this bigger, but I have different options of choosing. Since this is already formatted in NTSF and has other operating system, it's not giving me an option to select different file systems. But if it was under normal drive, I would be able to select either different file systems, like there is NFTS, there's FAT32, there's EXFAT, etc, etc, etc. So I would go ahead and format it and give it a file system, which will enable my operating system to directly go ahead and play with my disk. So at the same time with creating logical unit numbers is basically formatting. The same thing that you would come here and do in your operating system, and you'd be like, as you can see, my partition C here has has more than 1, 2, 3, 4, has 4 logical unit numbers, or what you people call partitions. So I partitioned it here. Actually, it self-partitioned itself with the EFI system partition, basically to do with the, data recovery and all that and all that. It also has a health recovery partition, and also this was for, I think, Ubuntu. Sometimes I dual boot my machine, and yeah. So this is my primary drive, which has my operating system and all that, and then I could be able to get into details and see its details. So if I wanted also to create a logical unit number, I would just go ahead, and then I will go ahead and partition it, or maybe shrink the volume to create space, and after go ahead and partition my drive. So basically what you're seeing here, I have only 2 drives on my machine, but I was able to create different logical unit numbers on my machine, so that my operating system can be able to access some of those things. So we want to look at virtualization storage conversion path, and try to understand what that virtualization path is. Like we said already, this video is going to make it a bit, or this animation is going to make it a bit more interesting. You can see we need to first, read or replicate our drives, and after reading or replicating our files now are converted into our physical volume. And then the physical volume here, now we can create partitions, or what people call logical divisions or logical unit numbers. And after that, then we come up with our logical unit number. And then after having our volumes, then we can now format it and give it a file system. The file system, for example, like the NFS file system, and then we can now go ahead and attach it and mount it to a cluster, and then boom, we have a virtual file system, and our virtual machines can access this shared catalog to have access to our storage devices. In a non-virtualized environment, or non-virtualized storage conversion path in cloud computing, basically still we do read or replication. At the beginning, we have our physical drives which we convert, and after putting them together like in an enclosure, we have our physical volume. And that physical volume, from there and there on, we create our logical volumes. We then have our logical volumes, and now we can attach these. When we attach these will not be attached to our virtual machines as folders, but they'll be attached directly as logical volumes, and we shall get into those details later on. And boom, we have our virtual disks that can be accessed and manipulated by our virtual machines. But before now we talk about those things of smart reading, I hear virtualization, I hear replication. We now want to understand some of the different types that are related and the different techniques that are related. What are some of those disk types that we can use? I know many of you know those disks, and some of you, those things are not alien to you. Maybe if I could get a volunteer to mention some of a few disk types that you know.
Yes, Mr. Sandy.
Yes.
Mic check.
SSD.
Yes, we have SSD.
HDD.
SSD, very good. HDD.
We have IDE.
We have PATA. Though some of these could also qualify to be, SSD. We have SATA, we have nearline SATA, we have SAS, we have etc, and we're going to be looking and drawing our attention to some of those important drives that we should, know. So let us look at the physical disk types, and in this case, we want to first look at SATA. SATA is very common to us because of these interfaces, and there's its brother, which usually people use to call IDE, or what equivalent to PATA. And this was dropped in the due time because of its disadvantages, the slow speed and writes, limitations, and of course also the interfaces. The more you plugged it in, they had issues, and so that's why people decided to come up with what they're calling serial advanced advanced technology attachment, which we are calling SATA. So it is also called serial ATA, and it's a computer bus interface that connects host bus adapters to mass storage devices. Using serial connections, the serial ATA uses embedded clock signals to check transmission commands and automatically corrects, detects errors, ensuring reliable data transmission for SATA disks. The SATA interface is simple, and the disks are hot swappable. Many of you, I think those who have got an opportunity to get into the hardware and to get an opportunity to see what or how hard drives looks like, I think you have seen many of these drives, and we use so many of these drives to date. You agree with me? So this is what we are calling SATA. And SATA, inside it, the hard disk, the what most people call HDD, has a platter and a magnetic head, and which keeps on spilling and keeping the data, and a motor and rotating, and our data is there. It has an entire mechanism, and it works in that way. So having that entire mechanism, it means that it's not it's not prone to shocks. If it fell down, it can easily, and also data can easily be lost on such a hard drive. So this is what we are calling the HDD. So we also want to draw attention and come to SAS. We have SAS here. SAS is what you're calling the serial attached SCSI, or what people say CSCI, SAS, and it's a new generation SCSI technology, which, like the popular serial ATA, also uses serial communication to achieve higher transmission speed. And compared with the older parallel SCSI, SAS improves the efficiency, availability, and scalability of storage systems, and offers optional compatibility with SATA. Now, the good thing with the serial attached ATA SCSI, or what we are calling SAS, the serial attached SCSI, it gives us a more improved speed and read and write speeds, better speeds as compared to SATA. But its disadvantage as compared to SATA, it is quite more expensive as compared to SATA, and also because of its architecture and the way it was designed, it has a relatively low capacity as compared to SATA. So that's why it's not very popular, because it's expensive, and also because it has low capacity. It cannot go to some extent like SATA, and that's why SATA is still also very used to date, and this is not very, very popular, and it is mainly used in major scenarios where we really need a drive that is going to process faster read and write operations, like, let's say, in military or some scenarios where you use such kind of technology. So these guys, since that had those limitations, they're like, okay, because of capacity, and we can't afford to have that disk which is having that capacity, let us come up with what we are calling the nearline SAS. The nearline SAS basically is a combination of SAS interface with serial disks. Like you can see, they've got the SAS interface here, and they have combined it with our original disks that you can see. And you can see even this disk particularly has 4 TB in the example that they have used. So this is what we are calling nearline SAS hard drives. It is a type of hard drive that lies basically between SATA and SAS. And compared with a SATA drive for it, and SAS hard drive, it has a higher read and write, although it has also a higher price. And having the higher price also, that means that it also has some kind of smaller capacity as compared to SATA. These drives were developed. They basically combined the interface for for SAS, and also the interface for SATA, to come up with this kind of drive. Now, the rotational speed of this drive is about 72,000 RM, so the performance is lower than that of SAS disks. However, the SAS interface addressing the speed improved. So Yeah, let us look at another type, which we are calling SSD. SSD, like you hear its name, SSD, it means a solid state drive. And to date, many people are opting for SSDs, by the way. And it's a solid state storage device that uses integrated circuit assemblies as non-volatile memory. An SSD consists of a control unit and, of course, storage unit, the flash, and the DRAM chip. An SSD is the same as common hard disks, the HDD that you see in terms of interface and even the way it looks. Sometimes you can see them, and sometimes you can even be hardly barely get a very difficult, moment to differentiate, unless maybe if you have carried it, you also come to realize that SSDs are slightly lighter as compared to HDDs. They're not heavy because of the way they were built. So in terms of interface specifications and definition, functionality, usage, and products shape and size, they almost look similar. So although SSDs deliver high or fast read and write performance, they are also lightweight, they also consume low power, and they're also smaller as compared to our traditional HDDs. But because of the way they were built and because they were built on chips, they have a shorter lifespan, and of course they are more expensive as compared to the traditional HDDs. Those who have bought a 1 terabyte drive of HDD, how much did you buy it?
108.
Yes, here in Uganda, it's around from 150 to about 200, depending on where you buy it. Some people even said it's 250, depending on where you have bought it. So those who have bought a 1 TB SSD, how much did it cost you?
700.
700?
In Nigeria is about 25,000 naira.
Nigeria, it's about 25,000 naira. If you can also tell us the traditional HDD, it's about what? How much in Nigeria?
15,000 naira.
It's about 10,000 naira. As you can see, according to the prices you have told me, this guy almost doubles, the SSD almost doubles the price of HDDs. Why? Because it's going to give us all these abilities of higher speeds, and that's why gamers are opting for SSDs, lightweight, low power consumption, and of course compact sizes. They are smaller as compared to HDDs. This is what we are calling SDDs. But however, HDDs have an advantage that in terms of capacity, only that to date these guys have just tried, but you can notice that some of 1 TB, 2 TB, 5 TBs, they're not very, very common as far as SSDs are concerned, isn't it? But HDDs, you can find really, really huge drives on the market. So HDDs give you more capacity as compared to SSDs, whereas SSDs give you more performance as far as read and write is concerned. Also, if you want to keep data for a very long time, it is advisable that you opt for HDDs because they have more lifespan as far as reading and write is concerned, whereas the SSD have a relatively shorter lifespan as compared to HDDs. So comparing
Mic
these,
check.
Yes, please.
What range is the lifespan in number of years?
In number of years, it entirely depends, but I'll ask you on that note to go and utilize Google. I think Google will help you with quite a number of material. Yes, it also varies on the manufacturer, but you can go ahead and read more about the lifespan. And sometimes it's also based on the number of read and writes, the number of times you have accessed the device. It's also sometimes measured according to that, not necessarily years. But you can go ahead and utilize Google and make full use of it. So, yes, please.
I think it depends also how you use the computer, because I bought new one. It took me only 2 months. It got corrupted. So it depends on how you use the computer and the drive.
That is also true. So it depends on the number of times you're going to read and write from the hard drive. And let's say if you're always reading, maybe it's a disk that people are accessing to read and write all the time. So it also depends on what your intended goal is. So we have here our performance, and as you can see, our what would be, maybe if I could just ask, what gives you a relatively low performance, and the price is also relatively low? What would be that?
ID, I guess.
HDD. Okay, according to what I've explained, what gives you a relatively better performance, and it's also expensive as compared to HDD?
The solid state drive.
Solid state drive. Okay, what gives you a better performance, and also the price is extremely high, but it has low capacity?
SCSI.
Is the SAS.
It is
SAS.
the SAS. What is extremely gives you best performance after combining the SAS technology and the and the SATA technology?
NL SAS.
Airline SAS, and its price is extremely very high for you to be able to implement. So ladies and gentlemen, at this point, want to look at the differences between centralized storage and distributed storage. Like you hear the word centralized, basically it means that all storage resources are centrally deployed and are provisioned over a unified kind of interface. You have your disk enclosure somewhere, and all your computers here are accessing resources from these enclosures. All the computers that you have, all your servers are accessing storage from that kind of architecture. So all the disks are centrally deployed in one kind of enclosure, and they are used to provide resources and services externally through what they are calling an enclosure. So a centralized kind of storage is typically referred to also what they are calling disk arrays. Okay, so we can have our disk array, and disk array you could be either having it is SAN or it is NAS. We're going to be looking at these things later on, and these things are going to help us, RAID all our disks together and put them together. It could be a device and you have quite a number of disks inside, and they're going to bundle them together and after give us a RAID. And after giving us a RAID with a band of physical volumes, and then our machines, after we get a storage pool from that RAID, and then our machines now can read and write data from that storage pool. The importance of that it can even just come here, open your enclosure, remove the faulty disk, add there the new disks, and then you are not going to affect the reliability of these machines, and business is going to continue working as normal. So the best main categories we can look at is the NAS and also the SAS, the SAN. When it comes to the SAN, basically, it is what we are calling the storage area network. We shall look at it in details, and it uses blocks as the basic data units. And the centralized storage uses these two that I've told you about, NAS and SAN, and SAN can furthermore be categorized into depending on how you're going to access it. If you're going to access it over an IP address, then we're going to categorize it to be IP SAN. If you're going to access it over a fiber cable, then we are going to call it the fiber FC SAN. So depending on how you're going to access it, and today engineers are also trying to come up with a better way, because fiber is quite expensive and it's also difficult to implement. And so they are trying to come up with a better way of how they can, use the fiber cable, fiber channel over Ethernet. And that's why we shall have the fiber over Ethernet SAN. And we shall be looking at these things in detail. So basically we have our disk array, which is going to combine multiple disks into a single logical unit, the logical unit which you're going to have here, and then our servers can access those resources from that logical unit. And this disk array consists of one controller enclosure, like you see this controller enclosure, and it can also have multiple disk enclosures inside. So the architecture delivers an intelligent storage space featuring high availability, high performance, and also high capacity. Okay, basically. So if it is IP SAN, like I told you, IP SAN, you can be using IP to be able, you use your normal, IP protocol, TCP IP, to be able to access the storage devices on the network. And we shall be looking at those things later on in detail. So basically, this is centralized. You have one centralized point which reads our drives that are enclosed here within our controller, and these guys are converted, and we have our storage pool, and our servers access those things. Like before, because we have talked about RAID, now we need to make ourselves more conversant with what a RAID is. Before, because you're talking about now, you go ahead and raid our disks and raid them. After raiding them, so now we want to be able to understand what are they meaning when we are talking about raiding. So let us look at the next few slides and try to understand what raiding is. Okay, so before even we talk about it here, they're telling you that trading helps you to have efficiency as far as parallel read and write on disks, all on multiple disks, and also it gives you safety, that your data is secure by doing parity check, and of course you can also do hot backup of your data. So this is RAID, and we're going to look at them. There are seven types or categories of RAID, ranging from 0 up to 6, and depending on what you want to achieve and depending on the need or the task at hand or your environment, you can use that technology. So we are saying here that in a centralized storage system, all disks are put in this guy, what we called an enclosure. I'm not seeing my pen. Okay, all these things are put into one enclosure. This enclosure, which is going to be having all our disks inside in a centralized kind of storage architecture, and they are uniformly managed by an enclosure. And that system supports dynamic storage capacity expansion, and also it helps us to improve fault tolerance as well as read and write performance. Such a system typically uses technology called the RAID technology, and in full, it's what we are calling the redundant arrays of independent disks. You have independent disks, and it's an array of independent disks, and you have put them there in a redundant mode and want to understand. And we said there are 7 types, but in this particular course, we're going to be focusing at RAID 1, RAID 2, at RAID 0, RAID 1, and RAID 5, and RAID 6. Those are things that we are going to be focusing at. So let's look at the first RAID, which is RAID 0. With RAID 0, it also has another name, which we are calling stripping. And it combines multiple physical disks. As you can see, disk 1 and disk 2, it combines these different multiple disks into one kind of logical disk, which delivers the highest storage performance amongst all RAID levels. And even though we have 2 disks here, it's going to get all the disks that we need, and it's going to combine all these disks into one logical disk. Now it's going to give us the best storage performance, because if we have, for example, disk 1 is 1 TB, right? And disk 2 is 2 TB. In total, we are going to have our disk of 3 TB. Our entire capacity is going to be having 3 TB. But now look at it, that our data, for example, we have 2 disks here, and the way our data segments are going to be stored. You see, as our data is being stored, we have data 1, data 2 of the same song. Think of this is our MP3 song, and we want to store it on we are storing it on our devices. And as you can see, it's going to get one part on disk 1, the other part on disk 2. The other part on disk, it's going to strip it and store it on the different disks. Now, think of it that one disk is faulty. Do you think you'll be able to access your song or even recover it and play it?
No.
Your data
No.
will be lost. Your data will be lost. Very good. So that means that this kind of RAID gives us actually no redundancy. There's no data protection, right? If one disk is dead, there's no data redundancy. So that is RAID 0, and you need at least 2 disks to be able to implement it. Let us now look at RAID 1. And with RAID 1, it also has another name which we are going to be calling mirroring, okay? Another name which we are calling mirroring. And with mirroring, it is designed to maximize availability and repairability of user data. For it, what it does, it automatically copies whatever data is on this disk to all the other disks that are within that RAID. Whether you have 3 disks, it will copy the same data here to there, to here, to there. So it gives you the best redundancy. And as far as data backup is concerned, it gives you the best data security. You know that even if one disk died, at least you can always recover your data and retrieve it from other disks. The moment you replace that faulty disk with a new disk, then all your other data will be now copied to this. As you can see, this data to here of your song has been mirrored to there. Also this mirrored to there. So whatever content is on this drive is also the content on that drive. However, this disk has an issue. This kind of RAID technology has an issue, that the total number of capacity you have in your RAID, whether you have 20 devices, whether you have 20 hard disks or 30 hard disks, it will only be the total capacity of the smallest disk in that RAID. Is that clear? So whether you have this one
Yes,
is
sir.
2 TB, this one is 1 TB, and this one is 2 TB. In total, ideally, if we are using RAID 0, we would have a total of 2 plus 1, that is 3 plus 2, that is 5. But since we are using mirroring, it will be the total of the smallest disk in that RAID. So meaning our total of the logical drive we can use, this logical drive here, its total capacity will be equal to 1 TB. Does that make sense? But our data is very secure. And even if this drive crashed, we can just remove it, hot swap it out, put there another drive, and then all our data is copied onto that drive which we have just replaced. So it gives us the best, data security, but of course it has a very poor performance as far as storage usage or performance is concerned. So to address that issue, they're like, okay, it has come up with RAID technology 5, what we are calling RAID 5. And RAID 5 is one of the most commonly used technologies. Why is it the most common used technology? Is that because it uses some kind of superior performance and data redundancy balance design. The way it was designed, you can use independent data disks with the distributed parity, which parity is going to be used to check for parity checks and error corrections. And you're going to use this parity to be able to, to recover your data. As you can see here, the minimum disks you can have in RAID 5, 1 are 3 disks, and 2, it gives you a redundancy of 1 disk. You can afford failing 1 disk, right? 1 disk can fail, remove it, and then replace there another disk, and it's going to use this parity checks, parity, things that it has stored together with your data to be able to recover your data. It knows that, for example, if I'm going to use this kind of equation, that I have these parity checks, and I know for me to be able to get the remaining data, I can use them to know the remaining answer. For example, if they told me 2 plus, let's say x is equal to 5, right? So even if I don't know this parity check here and the disk is lost and I put it in back, I am able to automatically using this algorithm to calculate and tell, oh, actually this parity check was supposed to be 3 to be equal to 5, isn't it? Right? So I just replace my disk and I know that the parity check is 3. Even if this was lost now, I know 2 plus 3, I have the 3 available, right? But I don't have the 5. The 5 is not available. I know it is an X, but I know when I add 2 plus 3, I'll get my 5. So the parity check here is supposed to be 5. Even if I didn't have, and I have my 5 here, I don't have the 2 here. It is an X. The disk got faulty and removed it and replaced it. Basing on that parity kind of technology, I'll be able to recover and repair and restore my data. So this kind of technology gives us one of the best superior performance and data redundancy with balancing in design. So you're balancing both storage capacity and you're also balancing the idea of data security. So here you're only losing one drive or one. It gives you a redundancy of one disk. You can afford to lose one disk, and then after when you replace, you can be able to restore your data. But in case 2 disks failed at the same time, you will not be able to actually get to know what this parity check or be able to recover your data and that parity check. That's why in some instances, engineers decided to come up with what we are calling what you're calling RAID technology 6. But before that, we are saying RAID 5 is a storage solution that helps us to balance both the performance. You are able to maximize on the storage performance. 2, you're also able to maximize on the security of your information. You know, you have a redundancy of at least one drive. Even if it was faulty, you can remove it and then replace it there, and then you can be able to access it. And 3, also it is cost effective. The storage costs are minimized because this almost does exactly what this to help you recover your data. But this one, even if you have 20 drives, I mean, your total capacity will be the capacity of the smallest drive in your capacity. So meaning for you to access and be able to store a lot of data, meaning you have to buy so many drives and to fill it in. But even if you did so, I mean, you'll not be able to get the best use as far as costs are concerned. So you're wasting resources. You have 5 drives, and as part of all those 5 drives, the only capacity you can get out of RAID 1 is just the capacity of one drive. That is also a bit somehow unfair. So that takes us to RAID 6. And with RAID technology 6, this mode is designed to further enhance the data protection that we have been looking at here in the previous chapter. And also compared with RAID 5, RAID 6 has an independent parity block. This way, each data block has 2 parity blocks. It's going to check using those 2 parity blocks, and it can use those 2 parity blocks to be able to, to do the verification of information and also to allow data loss on 2 disks in array, that you can afford losing 2 disks in array and you are still happy that you can actually replace those disks and your data is not lost at the same time. So this one also helps you as far as data security is concerned. RAID 6 is higher than RAID 5. Even if 2 disks in an array failed like that, the array can still work and recover the data from the faulty disks. But the design of the controller is more complicated and the write speed is lower, and it also takes a longer time to calculate those parity checks in this kind of technology, to check the information and also to verify the data correctness. It takes longer. So when the write operations are performed on each block, 2 independent blocks need to be calculated. This results in taking a lot of resources, and in addition also the disk usage is lower and configuration is also more complicated. Therefore, RAID 6 is applicable to an environment that really necessarily requires high data accuracy and integrity. But if that's not the case, usually most people use RAID 5, and it is commonly used because of its advantages that we have been able to discuss. So
Pardon me, Mr. Sende.
Yes, please.
Kindly mute everyone who's talking in the background, and if you can kindly disable the chats as well, we highly appreciate it.
Okay, I will do that now. Kindly, please keep your microphones muted for us having a smooth, conversation, and also to enable our class to go on without interruptions. So these are the different types of RAID.
Check.
Yes.
Sorry, Mr. Sandy, about the mute, disabling the messages. I think some people were trying, sometimes if you are not clear about something, we are asking questions and we are being helped mostly by Joseph and the colleagues to answer some of the questions that we are not clear on and whilst you are explaining. So I think for the messages, you can leave them and you can disable the mics.
Mr. Sandy, mic check. I think it's disturbing. Why can't you take note of those questions and you ask at the end? It's disturbing. We have to, because it just flashes on the screen.
We're saying that in a centralized storage, what did we say in centralized storage? What happens? Can someone remind us? Can someone remind us, what did we talk about in a centralized storage?
It's kept in different disks are put in this group, and then the virtual devices,
Okay, you've all spoken at the same time. I didn't get what you're saying, but basically we said that all the resources are centrally deployed in some kind of enclosure, unified interface. All other physical, machines are able to access these resources from this centralized storage device. They're all accessing them in a way or in a centralized manner. So we talked about SAN.
Mic check. Sorry, Mr. Sandy. There was some interference when you were explaining the centralized storage types, so we couldn't hear anything.
I said with the centralized storage, all the storage resources are centrally deployed and they are provisioned over in a unified interface. So all of them are put in some kind of disk array, and all physical disks, they are centrally deployed in enclosures. It could be any provisioning company which is giving you that disk enclosure, and all your disks are provisioned there. And now all other physical computers or other machines are going to be able to access those resources from that particular central thing. Okay. With this distributed, like you hear the word distributed, you have different resources that are distributed, and machines are sharing them in a distributed kind of way. And we shall be looking at that in the near future. But basically, I'm just telling you about centralized, so that you remind yourself that we have one central point and all resources are being accessed from that central point. We said we have SAN and we also have NAS. When it comes to SAN, this is what we are calling the storage area network. The storage area network. And with a storage area network, it is a storage area network, SAN, with blocks as basic data units. And it is a dedicated high-speed storage network. Like you hear the word storage network, it's some kind of network. It's a dedicated high-speed storage network that is independent of service network system. It doesn't really depend on your service network system. It has its own dedicated kind of network. And this type of network is implemented in form of fiber channel storage area network. And sometimes what we called the FC SAN, the fiber channel storage area network, or it can be implemented using the IP SAN, what we're calling the Internet Protocol storage area network, or it can also lastly be implemented using the SAS SAN, depending on how you are going to be able to access it, or what we are calling the serial attached SkySkis storage area network. So there are different ways of how you can implement it and transfer data and commands and status between the servers and storages, but you can use such protocols like communication protocols and connections to be able to access network and storage from these devices. So a SAN, what it does, connects these isolated, these isolated storage islands through a high-speed kind of network. And these devices can be shared on multiple servers through the network, thus enabling us to have a remote data backup and excellent scalability. All factors make this storage technology develop rapidly because it can be accessed over the IP. And almost all networks today use either a combination of IP and the fiber channel kind of communication. So the SAN is basically network architecture, and that consists of storage devices. Like these are the storage devices and the system components, including the servers that need to use storage resources, hot buses that connect storage devices, and fiber channel switches. That is what we are calling the SAN. So if we have used the fiber channel switch, then that means that we also need to configure the interface adapters for this kind of network to be able to access or use our storage devices. The SAN delivers high input or output capabilities for the entire network, and it also helps us in reducing data network efficiency of the original applications, and also providing us with redundant links to our storage. And also it supports high availability. We shall look at some of those functionality in the next chapter, which is called virtualization features. So IP-SAN has become a popular, this guy here has become a popular storage network technology in the recent years because it connects via the IP protocol, and customers who want to implement fiber channel SAN, remember originally fiber is quite expensive, its high price and complicated configurations made it very hard for small and medium-sized enterprises to implement it. So it only focused on mid and high-end storages that require high performance, redundancy, and availability. So for these guys to popularize SAN, they made sure that they also come up with an architecture that supports IP, and that's why IP-SAN that uses our existing IP networks architecture, they were introduced. It uses a combination of our standard TCP IP protocol together with our SkySkis instruction set, and it implements a block level data storage based on our IP network structure. Okay, that is what we are calling the IP-SAN. Basically, the difference between fiber channel and IP SAN is it lies on the medium they're going to use, and also the protocols they're going to use to transfer the data. As you can know, FC SAN uses which medium to transfer the data? Who can guess that obvious question?
Fiber.
Fiber, very good. How about IP SAN?
Ethernet.
Network. Ethernet.
Okay, it uses Ethernet.
It can be Ethernet, it can be Wi-Fi.
IP network architecture.
Okay, it can be Wi-Fi, it can be any other medium to support the IP or TCP protocol. And some of the common IP protocols, they include the SkySkis.
FCIP.
They include FCIP, very good.
IFCP.
IFCP, very good. And yeah, so basically that is the IP SAN. It has the advantages because it's using the common IP kind of network. It has a standard access. As long as you're on an IP network, it's easier for you to access it. Because IP travels in a very long distance, because of the TCP IP protocol, we are able to communicate with people from Nigeria, with people from Zambia, with people from TZ, Kenya, Uganda, etc. So it also facilitates long transfer distance. IP signs are available wherever IP networks exists. And currently IP networks are the most widely used networks in the world. You will all agree with me. So that is what we are calling the IP, or that we are calling the storage area network. Let us also look at the NAS, what we are calling the network attached storage technology, network attached storage network technology that integrates a kind of distributed and independent data into large and centralized data for access by different hosts and application server. For it, it's a file level computer data storage connected computer to a network provisioning data access or homogeneous group of clients. It's more like a server. Think of it like it's a server with disks inside providing storage resources. So a NAS server contains storage devices such as disk arrays. They could be even CD drives. They could be anything, and they provide it to you. It could be portable storage media, and then these devices are put together to deliver a kind of embedded operating system to share files across different platforms. You can share files on a Unix platform like Linux, Mac OS, and also platforms like for Windows. If you're going to use a Unix platform, you use a file system called the NFS. If you're going to use Windows, you're going to use CIFS, which is Microsoft, Microsoft file system, usually implemented by SMB, server message block, to help you or to help us have some kind of, cross-platform sharing of data, same time also data security. So one thing you should take out of this, NAS is a file system based kind of technology. It comes with a file system embedded on it, and you're able to access the files on the network. This is a block level, and for it you access the disks that are available to you. Here you access the disks in form of a hierarchical structure, like folders, right? You access your storage media devices like folders, like how you would access your folder on OneDrive. Whereas here you actually access your drive directly because it's a block level kind of architecture. So this is NAS for you, and we are calling it the network attached storage technology. And it can be used on Windows client. It can also be used on Unix, like clients like Linux, like Mac OS, and etc, 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 etc. So NAS typically has its own nodes on a LAN and does not require the intervention of application servers because it already comes with its file system. You do not need to go ahead and go through the process of having to configure like the way you do on a SAN for you to be able to access some of those different file systems. Some of the file systems I've mentioned here, I've mentioned CIFS, I've also mentioned NFS, and the CIFS is basically a public and open file system that was developed by Microsoft's Microsoft Server Message Block, and the SMB is a file sharing protocol that was set by Microsoft based on NetBIOS. Users can access data on a remote computer through the CIFS here, and CIFS here helps us to prevent read and write conflicts and write conflicts to support multi-user access. So we can use the CIFS to avoid conflicts and also to support multi-user access. So we enable Windows and Unix computers to share resources and enable Windows to use resources on a Unix computer as if they were on Windows NT servers. The best way to install and software that supports SMB or CIFS protocol on Unix computers. You know that different computers operating system have their own file systems that they support. For example, on Windows, what are some of those file systems that are supported by Windows?
EXE.
Yes.
FAT32.
FAT32. Okay, some of your network is bad. We have FAT32.
FAT, NTFS,
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 SMB, CIFS, Common Internet File System. We also have on Linux, what do we have? Those people who use Linux file system. Come again. Okay, yeah, some of your network is really bad, so I'll just move on forward.
EXT.
EXT. Please mute your microphone. If you have noisy background, I think Isaac, just go ahead and mute your microphone. Okay. So they all support that kind of system, and also the network file system that is supported on Unix. Basically, it's called the network file system. The NFS is a distributed file system protocol originally developed by Sun Microsystems. It allows a user on a client computer to access a file over a computer network, much like as local storage, the way you access your folders on your computer. So basically, that is a CIF. Basically, the difference between CIFS and NSF is that when it comes to transfer characteristics, CIFS is network-based, requiring high reliability. NFS is independent transfer. In terms of usage, it requires no additional software. This guy requires dedicated software to access those files. In terms of security and redundancy, fault recovery is not available here. Here you can be able to recover from fault. And as far as file conversion is concerned, you need to file format, not reserved. Here the file format is reserved of the files that you are trying to access. So moving forward to distributed storage, we have already talked about distributed. What comes to your mind? Any volunteer when you hear the word distributed?
Shared.
Mic check.
Someone has said shared. Yes, you have said mic check. Go ahead.
They are across the networks.
Across networks.
Mic check.
Yes, please. Lastly, go ahead.
From my understanding, is basically doing segmenting storage areas.
Segmenting storage areas. Thank you. So virtualized storage is quite different from the way or the conventional storage. What it does, it virtualizes all available space distributed across different hosts into a single kind of virtual device. Like all these hosts are, distributed. This could be in Nigeria, this could be in Zimbabwe. They're distributed, but they all come up to access or to provide resources towards one kind of a virtual device, which will be all accessing somewhere in the cloud. So it is these guys who are actually using their own resources to actually come up with a kind of virtual pool, which they will actually go ahead and access those resources. So the data stored in this virtual storage is also distributed all over the network. That data which is stored here will be replicated and stored here, replicated, stored there, replicated and stored there. In that, even if this server died, you could easily replace it, and then the data replication takes place. Let me play this animation. So we have all these, let's say, storage servers, and we have distributed them across our networks. They have their storages, they have their hard disks inside them. So we're going to do replication of those storage devices, get all those devices in these computers, and then put them together in form of replication. And after replicating them, we are able to come up with our distributed kind of shared storage pool, where now all these guys are going to access, read, and do data read and write. So the storage resources you have seen there are a distributed storage system that come from these normal servers rather than coming from a dedicated storage device. That's the difference. And a distributed storage system has no controller or disk enclosures. Have you seen there physical servers? So the clients delivered by distributed storage systems are responsible for making sure that they identify and also manage disk drives, establish the routes, and going to at the same time go ahead and execute the read and write procedures or activities. So in terms of capacity expansion, it is easy for us to be able to install or expand our capacity, giving us great reliability. That even if I wanted to increase on the capacity, I would just add another host onto this distribution to provide also his resources here. I also go ahead and add another storage server and then provide. So it is easy for me to either scale in or scaling out of that kind of distributed. So keyword to note, it's distributed across networks, and we do replication of data. And after doing replication, at that point we are able to come up with that distributed storage pool where now all our servers access and do the read and write operations on our data. So to ensure high availability and security of data, the centralized system also uses the RAID technology. And this is in the centralized system, and the RAID technology can be implemented by hardware and software. You have your RAID technology hardware, enclosures where you put your independent disk arrays, and then you're able to read those things and then come up with your RAIDed technology disks, logical disks, and then you're able to access data using that kind of security mechanism. But in distributed mode, for us to make sure that we have security and redundancy of our data, we use the replication mechanism. Which is going to keep identical copies of our data on different server, on server A, on server B, on server C, and on server D. It's replicating your data on those different servers, and the failure of one server will not, if server A failed, it will not cause failure on server B or server C or server D. So this distributed storage system combines local disk of all servers into one several resource pools or into all several resource pools, and based on the resource pools, then the distributed storage systems delivers interfaces for creating and deleting application volumes and snapshots, and delivers high volume device functions for upper layer softwares to use. So basically, we're using the replication mechanism to make sure that we achieve data redundancy in our kind of system. So replication, this is how the replication process works. Basically, we are going to get our data and we're going to send it on our distributed shared pool. And our distributed shared pool is going to, depending on the number of devices available there, it's going to go ahead and replicate that data into those copies you're seeing on the screen. And after replicating it, then it's going to go ahead and store it separately on those different disks across all our distributed physical servers on the network. By using this, we have then written our data. Now, accessing the data, the good thing about it, we don't have to necessarily go through the process of accessing or reading data from everything. What will happen when it comes to reading data? Only the active data will be read on from our distributed pool. That's not putting the load on all our hard drives, thus saving on resources and also at the same time improving on efficiency. So some of the popular distributed storage products, we have VMware, vSAN powered by VMware, we have Fusion Storage powered by Huawei, we have Hadoop powered by HDFS, and we have Safe. Those are some of the popular kind of distribution storages. So we want to look at virtualized storage versus non-virtualized storage. We already said that storage virtualization, the one we have talked about, we have a file system and we have our disks, which we are going to either RAID or replicate. And after RAIDing those things, we are going to come up with our physical volume, which are now going to partition and come up with our logical volume. And after coming up with our logical volume, now this logical volume, we format it depending on the hypervisor you're going to use or the operating system. Remember, you select the file system, for example, NT, FS, or EXFAT, depending on what you're going to use, and then you format it. And after giving it a format, we have our network file system. And then after giving our file system, you attach it to a cluster, and then you format it to have a logical virtual file system. So then we have our shared catalog, and our virtual machines can access the virtual machine disks from that shared catalog. In a non-virtualized storage kind of architecture, we are going to have our disks, which are either going to be RAIDed or we're going to do replication. And after doing that, we are going to come up with our physical volume. This physical volume is going to be partitioned, and we get our logical drives. And after getting our logical volume, we're going to go ahead and just attach this directly to our cluster. And then we have our virtual disk, which does not have a file system. Remember this, in a non-virtualized system, there are no file system, and then we shall be able to attach it there. So the logical unit number, I already told you, basically it is like you hear the word logical unit number, it is more like a partition, right? It is more like a partition, and it corresponds to volumes, like you hear the word volume, like those different partitions that you have on your computer. And usually volumes are managed in object system, and they are external representations, like logical representations of those drives, and they are allocated from the same resource pools. If you have your drive, like you're going to partition your drive, you're going to use that drive, and then you're going to go ahead and partition that drive accordingly. So relationship between RAIDs and logical unit numbers. A RAID array can be seen as a large physical volume made up of a number of hard disks. That is a RAID. And we talked about it, and we have different 7 types. And in this chapter, we focus on RAID 0, RAID 1, RAID 5, and RAID 6. We said, how many disks do you need to effectively set up RAID technology 0?
2 disks.
2 disks.
2 at least.
Do we have redundancy on RAID 0 or not?
No redundancy.
We don't
No
have
redundancy.
No, we don't. We don't
Okay. When it comes to RAID 1, how many disks do we need to effectively implement this technology? Minimum disks?
At least
2.
2.
2. Does it give us data redundancy?
Yeah,
Yes.
redundant.
It gives us data redundancy, but poor storage performance. And then when you go to RAID 5, how many disks do we need to effectively implement RAID 5?
3.
3.
3. And how many disks redundancy does it give us? We can afford using 1 disk.
1.
And we said it's most commonly used because it tries to balance the storage performance at the same time, high security to protect our data using parity checks. And we have
Exactly.
RAID 6. With RAID 6, we said how many disks do we need to implement RAID 6, technology 6?
4.
We need 4
There
disks.
are 4.
And it gives us how many redundancy disks?
2.
We can afford to lose 2 disks, and then we are able to recover our data. So you can mute your microphones. All thank you for participating. So on top of physical volume, you can create one one or more logical units. So on top of your physical hard drive that you have, you can go ahead and format it. And after format it, you can even create one partition or even more partitions. You agree? I want to explain it in that way so that it makes a lot of sense to you. So these logical units are called logical unit number, the LUNs, and can be mapped to hosts as basic blocks or as devices. Hosts will be seeing them as different disks. If I went ahead and partitioned my disks, the host will be seeing it as an external disk. Let me see if I can shrink this very fast. So if I went here on my computer and I went to disk management, where's disk management? And I went to disk management and it loaded, and I have my drives here. I have this, I don't know if I have space, and I go ahead and I shrink it. I go ahead and shrink it, and I go ahead and select that. I haven't really read through, but I go ahead and shrink it. I go ahead and select that to see the amount of volume it's going to leave behind. As you can notice here in this PC, I only have 2 drives at the moment that are there. It's taking longer, but as it's coming, let me just continue. Oh, okay, I have 2%. Wow, 2% free. Interesting. I need to delete some of the old recordings. Okay, we'll come to Zoom. Here where Zoom recordings are. Go to some of these olden things. Select some of them. And then go ahead and select. And then go ahead and delete. I've quite a number of devices, quite a number of things. Okay. So it is taking its time simply because I didn't check that it had 2% left, but I will continue with the class. So you go ahead and partition it, then you come up with your logical partition, right? Your logic, and it will appear to your operating system or to your computer as a block or as a basic kind of device. So you can either choose to format it, create multiple logic volumes on a single drive. You can either create 1 or even 2 or 3, or you can even go ahead and create as many as you want. That is a relationship between them. The process of creating it, you have your physical drive, your hard drive, your normal hard drives in your computer. You go ahead and RAID them depending on the technology you want to use. If you use RAID 1 and you have 1 TB here, you have 1 TB here, you have 1 TB here, and use RAID technology 1, what would be your total capacity of this drive? Of your logical drive?
1 GB.
3 GB.
3 TB.
3
If
TB.
you used RAID 1,
1 terabyte.
hey
1
guys,
terabyte.
it
Oh,
will be
1 TB. 1 TB.
it will be 1 TB. So you have our logical drive of 1 TB, but we know our data is secure. Even if this disk here died, we can still put in another disk, and then we are able to have our data back. So we have our 1 TB there, and then this TB now we can choose to go ahead and segment it and create different partitions and do the logical partitioning. On our computer now, it will appear as if we have, local disk D, local disk E, local disk F. I hope that makes a lot of sense, right? And then we have our logical volume. So the common network file systems, we talked about NAS file system. We also talked about, we talked about the file system in an operating system. What are some of them in Windows? You told me already. In Linux, you told me already. Some of those file systems that are common in operating system. So creating or mapping a file, please mute your microphone. Creating or mapping a file onto the disk. What is the process of creating or mapping a file onto? What is happening? Okay. Okay, so what is the process of mapping a file to a disk? So the user goes ahead, creates the file. After creating the file, it will be first stored onto our file system. Like let's say if you're on operating system, Windows operating system NTFS, stored there. Then this file system is going to help us do the mapping via the file system, and it will access the file system blocks, and it will map it on our logical volume locations, on our logic volume mapping. So after doing the mapping, it will go ahead and access the mappings on our physical location on our disks, move those different magnet segments, and then we shall have our disk sectors created on our physical drives. So that is a process of creating a file onto our system. So let us introduce ourselves to virtual machines. Let us introduce ourselves to virtual machines. But before we talk about virtual machines, I just wanted to talk about the two kinds of way of creating partitions. There's what we can call thick logical unit number and a thin logical unit number. Thick, it does not mean that it is big, but it also kind of relates to that. When we create it using thick, that means upon creation of this logical unit number, let me just wrap everything. We said we have thick and we have thin. So when you are using thick here, upon creation of this logical unit number, and when you're creating it, you say you want your device to be how many GBs? You say I want it to be 20 GB. Then it will go ahead and it will occupy all those 20 GBs of the physical hard drive upon creation. Whether you have stored files there or whether you have not stored files there, its entire total capacity will be equal to 20 GB, and it will go ahead and reclaim it from our main physical drive, and it won't be available. Even here, when you go back to check your physical drive, if it was out of, let's say, if it was out of 80 GB, it will show you that you have used 20 GB and 60 GBs are free. If it is thin kind of provisioning, with thin, you specify and say, okay, I want you to be 20 GB, but what happens, it does not immediately and automatically reclaim the storage. Your disk will still be 80 here upon creation, and you create it and it will even be displaying very well on your computer. But then it will reclaim storage on demand basis. The more you put their files, you put their movies, it expands. If it was 2 GB, you put their movie of 4 GB, it will increase to 6 GB. You put there something of 10 GB, it will increase to 16 GB. You go ahead and delete this movie of 6 GB, then it will reduce to 10 GB. Are you getting the picture? It will reduce to 10 GB. So this is thin, and also it has the capability of reclaiming data or taking back the storage that it has reclaimed from the hard disk. So that is the difference between thick and thin provisioning. So let us look at the virtual machine disks. So just like any other disks, this is you can, if you are using a virtual machine in your computer, you can also be able to see, and you see them and they will appear normally like any other, computer or disks. Like you see them like the one viewing my disks on my computer. You'll be able to see them and you'll be able to, manipulate and use them accordingly. In the administrator view, if you went to your CMD, depending on the operating system you use, and you go ahead and put in a command for you to be able to access your disks, then you'll be able to access your drive. So in this case, if I wanted to access my to access my disk command from my disk view, I would maybe open my command prompt, and in my command prompt, I say I go to, I think it is disk part. I've taken long without using these things. It asks me, are you sure I want to access the disk manager? And then boom, I will be, after a few seconds, I'll be inside disk part. It has not yet loaded. Oh, it has loaded here. So I'll be inside disk part, and then I can be able again and say, I don't know why it's not typing. I can go ahead and say, oh, wow, it has not yet responded. I think because of the process I gave it. But you can go ahead and say list disks, and you're able to see the different disks that are available to you for you to use. So these are some of the common disk virtual machine disk formats, and please pay attention to this slide. For most of the vendors, they support the format called RAW. And for VMware, it supports a format called VMDK. And if I went here in my where I store my virtual machines, and I went to where I keep the files, I go to virtual machines, I go to VMware, you will see the formats. I don't know if you're able to see the formats. So you see the formats of my virtual machines, which I've created. I don't know if I can make these things bigger and bigger so that you're able to see. So you can see that my last virtual machine I created, it is VMDK, and this is for purely it is for VMware, right? It supports the kind of file format of VMDK. These are the disk files or the file formats that are supported by VMware. And now when I go to Oracle, I don't know if I don't have any virtual machine for Oracle. I don't know if it's also there in program files. Okay, we shall look into that later on. But for Oracle, most of the Oracle we use VDI, right? To use VDI, and you'll be able to see the virtual machine for Oracle. For KVM and KEMU, and because also Fusion Compute is also based on KVM and KEMU. If they ask you for Huawei, it also supports QCOW or QUD. So KEMU and KVM virtualization platforms only support this kind of formats, and VHD is supported by Microsoft Hyper-V and Huawei Fusion Compute. They support the format of VHD. Okay, so Huawei, if they asked you the question for Huawei, I think it would support RAW if it was on the list. It would also support VHD. It would also support QCOW or QTED if it was on the list, because Fusion Compute leverages on KVM and KEMU to perform some of its, it was built on top of KVM. So storage features for virtualization products, for Huawei's virtualization products, we want to look at them. Like we said, we can have either a Fusion storage, or we can use NAS or SAS to offer us. We said Fusion storage is one of the most popularly used distribution kind of storage. And here we can have NAS or SAS for our centralized kind of storage. So upon this, then we create or we share our shared catalog. And upon this, you just go ahead and create a logical unit number, and then boom, you have your virtual hard disk ready for use, what they call the RDM. Here in a virtualized storage, you go ahead and you have your file system. In a non-virtualized storage, still you go ahead and access your local disk basically. So you have your storage resources, and depending on what you're going to use, you have your storage device created, and then after you create what they call a data store, and this data store are relying on your storage device, and the storage devices are relying on the storage resources, the physical real storage resources that you have on your network. So Huawei virtual disk features, these are some of Huawei's virtual disk features, and we want to look at some of them today and try to understand. As you can see, we have two types here, two popular types. We have common, and we also have shared kind of types. Now with the common, sometimes it's also called non-shared. Where's my pen? With common also sometimes it's called non-shared. It's common and it's not shared, and it doesn't want to be shared. So like you hear, if it is non-shared and it's common, it doesn't want to share, meaning it is only used by what? One virtual machine. Only one virtual machine can use common. It is non-shared. It doesn't want to share. It is pretty obvious. Like you hear the word shared. What does that mean? It can be shared across multiple virtual machines. All right. So we also have a different way when you're configured, based on your configuration mode. Virtual disks can be classified either on common or thin provisioning disk, or thick provisioning lazy zero disks. So when it comes to configuration mode, think of common as also thick. Sometimes they call it thick. And we talked about thick already. What did we say thick is?
Mic check.
Yes, please.
Yeah, thick claims the storage immediately, the space from the physical hard drive.
Yes, very good.
The space.
Yes, very good. So the system here, upon when you're creating the disk, it allocates disk space basing on the disk capacity. So during this creation mode, data remaining on the physical device will be zeroed out depending on the capacity you have specified on the hard disk, like I explained. The good thing with this kind of configuration mode, the performance is better than the other two kind of performance. But remember, because you are creating and reclaiming everything, the creation duration may be longer than that of the other guys. And also in terms of storage utilization, this process is not this kind of configuration is not advisable. And also in scenarios when you're not exactly sure of how much storage capacity you need for a given application to run or virtual machine, then this kind of configuration may not be advisable. So when we come to thin, I also explained it. Anyone to tell me what I talked about it?
Data is not instantly, the space is not instantly claimed for. It is only claimed for when you use it on the virtual device. If you use it, it reduces on the physical device. If you reduce it on the virtual device, it increases on the physical device, on the physical disk.
Very good. Yes, please.
I would simply say it occupies space on demand basis, and it also reclaims storage.
Very good. Thank you. So, and that is it. And the last one is thick provisioning, lazy zeroed out. It is not mentioned here, but there's thick provisioning, lazy zeroed out. Here, it is the same as thick, but only upon creation, it does not zero out the storage, but it zeroes out the storage when you first write the first file on that drive. Then it will go ahead and it will occupy and it will take all the storage from your hard disk. That is the third one. Now let us look at the different disk modes. We have independent, we have dependent, we have independent persistent, and we also have independent non-persistent. So with dependent mode, a dependent disk is included in the snapshots, and changes are written to disks immediately and they are permanent. Here, key things to take out of this: snapshot is included. We shall look at snapshots later on and try to understand what they are. They are included, and here also changes, they are written to the virtual machine, and they're written immediately and they are permanent with independent mode. When you create the disk in independent and persistent mode, here with independent, in this mode, disk changes are immediately and permanently written to the disk, just like this, immediately and permanently written to the disk. But then it is not affected by snapshots. So meaning snapshots here, they are not taken care of. They're not, taken. You don't take snapshots here. So meaning this mode is almost like this. Only difference, it does not support snapshots here. And then when it comes, or when you take a snapshot, disks are not. This kind of disks are not included part of that snapshot. With the independent and non-persistent here, the third one, in this mode, disk changes are discarded. Remember the other time, in the previous two, they're immediately written, but in this case, we are saying that they are discarded, and after the VM is stopped or restored using a snapshot. So when you create a snapshot and you want to restore this virtual machine, which you created, which was using an independent and non-persistent disk mode, the changes will be discarded and the virtual machine is stopped, and then it will be restored using, when you restore the virtual machine using a snapshot, all the changes are discarded. So you only select these two, independent and independent and non-persistent, when the system does not take snapshots of the data on the disk when creating a virtual machine. When you don't really need to take, you just want the configuration files, you're not interested in the data on that machine. So when the virtual machine snapshot is used to restore the virtual machine disks are not restored when you're using this tool and you're restoring a virtual machine using snapshots. We're going to look at snapshots and try to understand what they are in the next chapter. But if you're restoring snapshots using this tool, the virtual machine disks are not restored because we say the data is discarded in the process of stopping the virtual machine and also in the process of restoring the virtual machine using a snapshot. So here what happens after a snapshot is taken of a virtual machine, if the disk on the virtual machine are detached from the virtual machine and not attached to any other virtual machine, the disk will be attached to the virtual machine after the virtual machine is stored using the snapshot. But if, however, the data on the disk will not be restored if we have used this kind of two modes. So some disk types cannot be changed once they are set, and some can be changed. So yeah, I think that is all that you need to be mindful about, and some of those other things like snapshot, we shall be in position to look at them in the next coming slides. So this takes us to this quiz here. Which of the following disk types is recommended for an archive room? An archive room, usually they are storing data, and archive rooms, you remember, you usually store large amounts of data and also for a long period of time. So which of the following disk types is recommended for an archive room that needs to store large amounts of data that will be accessed infrequently over longer periods of time? Maybe you give me your answer and you tell me why you think your answer is correct.
SATA is quite longer. It is an HDD.
I didn't get you.
I'll take C.
SATA disk, that is C, because its lifespan is longer and it is an HDD. So it has a longer lifespan compared to all the others.
Okay. True. That is true. I will not repeat that, what he said. But the key word to use here.
Mic check.
Yes, please. Yes, Alvin.
Yes, I would take SATA because it is cheap, first of all. And secondly, it stores huge volumes of data. And secondly, I think that is all.
Okay, thank you, Alvin. Like all of you guys have said, that is true, because in this question, in this scenario here, we're going to store data in an archive room, right? And this archive room, we want to store a large amount of data. So already this puts this guy in lead. And of course, data that will be accessed infrequently, meaning I'm not concerned about, the high, read and write speeds. Not so. I'm not going to access that data frequently, so I'm not concerned about the high read and write speeds that SSD is giving me. I'm not concerned about that, and over a longer period of time. And I know this guy has more, has a longer lifespan as compared to SSD. And as compared to these other guys, one, these guys are expensive, more expensive as compared to him. And this guy will basically be the one who is most suitable for the job. That's why we go with him. Okay. SATA disks use parallel interface, while SAS disks use a serial interface. You give me your answer and you tell me why you think your answer is correct. The class goes quiet.
Mic check.
Yes, James.
I think it's false.
Why?
SATA disks use also like a serial kind of interface.
Very correct. No, in their explanation. Remember, we said serial is SATA is called serial advanced Come again?
Technology.
Yes.
Technology.
Yes.
Technology attachment.
Yes. Remember we say even by its definition, serial, and then I don't know how you can think that it is using parallel. You get it? So this statement
Yes.
makes it false, and that's why it leaves us with an answer of false. And ladies and gentlemen, that brings us to the end of this course, and you have looked at you have looked at how data is written on storage devices in a virtualized scenarios. You can go ahead and look at e-learning website materials for Huawei, and also leverage on the online forum to better understand some of that material. And thank you for being good participants, and also for effectively participating in the class. Thank you so much, and I'll stop the recording for
Mr. Sandy.